Designing efficient algorithms for visual multi-agent reinforcement learning is a goal that myself and excellent students at UIUC are excited about. I call those students the magicians. They are really the ones that deserve all the credit. They are the ones which make things work, and I essentially talk about their work. I argue that visual multi-agent reinforcement learning discusses topics that fit perfectly into the Embodied AI workshop. Indeed, in almost any environment, multiple agents interact, whether this is related to traffic, games, or indoor interactions. Moreover, I try to convince you that this is an exciting direction for future research endeavors, as a lot of concepts related to visual multi-agent reinforcement learning still need to be discovered, as I hope to illustrate today. Specifically, I will talk about permutation invariance and multi-agent collaboration and communication before concluding with a few pointers on future work. As mentioned before, visual multi-agent settings are everywhere. We are generally dealing with multiple agents. Agent I observes OTI at time t and is asked to perform an action ATI, upon which the environment changes and the agents receive a reward. The goal in any of those settings is to learn a policy pi, effectively a probability distribution over actions given observation OTI. We want to find that policy pi, which results in the highest expected cumulative future reward when performing the highest probability action across the observed observations. To make this concrete, let's look at an example. Suppose we are controlling two agents, each of which perceives the world from an egocentric view. We use the variable OTI to refer to the images, their observations. The agents react to the observations O by generating a distribution over the action space, which is done by the policy pi. The history of the previous observations and action is captured via ht-1 in this case. From this policy pi, actions are sampled independently per agent, which, after being performed by the agents, leads to new observations OT+1 for each of the agents. In this example, the agents lifted the TV. Note that independent sampling of the actions is suboptimal, which we address in recent work, but I will not focus on this here. Instead, I want to look at training of these systems. For training of multi-agent systems, we often use a centralized critic queue, which depends on all actions and observations and assesses suitability of the current configuration. This centralized critic has been remarkably successful because it helps to address non-stationary environment issues caused by the existence of multiple agents. However, prior work implements the centralized critic usually as a multi-layer perceptron. What does this mean? Imagine we have 4 agents, and let me illustrate the concatenated action and observation of each agent with a different shape: a square, circle, triangle, and a pentagon for the first, second, third, and fourth agent. Prior work now concatenates all these representations into one long vector, which, after being processed via a deep net, results in a scalar assessment of the current configuration, value v in our case. What's the problem when doing this? Consider environments with homogeneous agents. If you permute the agent positions, the environment is exactly identical. Nothing changed. But multi-layer perceptron critics don't necessarily assign the same value to permuted inputs. That's a problem. MLP critics need to learn permutation invariance from data. And this wastes a lot of data, particularly if there are a lot of agents, essentially exacerbating a sample complexity of multi-agent reinforcement learning training. How can we fix this? To fix this, we propose the Permutation-Invariant Critic. As the name suggests, we may permute the agent's ordering without changing the assessment obtained by the critic. To obtain a provably permutation-invariant critic, we represent agents via a graph convolutional net. Irrespective of the permutation, the output is identical. We can augment this network to consider heterogeneous agents as well, and I'll refer you to the paper on this topic for details. Instead, let me show you how well the Permutation-Invariant Critic works in multi-agent settings. We run experiments on the multiple particle environment. This slide shows one of the tasks with 6 agents. In this task, the agents work together to push the big ball, illustrated in darker green, to the landmark, depicted in light green. The left is a multi-layer perceptron critic result, and the right is a permutation-invariant critic result. We can clearly see that despite identical training, the permutation-invariant critic was able to better understand the task. But we are not limited to just 6 agents. In addition, we scaled the multiple particle environment to hundreds of agents, which did require to rewrite parts of the environment to make it more efficient. In this task, red agents have to capture faster moving green agents. Again, we observe the multi-layer perceptron critics to take significantly longer in solving the task compared to permutation-invariant critics. Let's quantify this benefit. To do so, let me show you some training curves. The y-axis indicates average episode rewards. The x-axis indicates the number of environment steps used for training. The blue and orange curves are multi-layer perceptron critics with and without data augmentation. The green curve is the devised permutation-invariant critic. Our permutation-invariant critic consistently achieves better results, particularly if the number of agents increases. This is to be expected as the number of permutations grows exponentially with the number of agents. Hence, we expect the permutation-invariant critic to perform much better for a larger number of agents. As I mentioned before, in order to scale to such large number of agents, we had to improve the implementation of the original multi-particle environment, which now supports up to 200 agents. For training 200 agents, the original multi-particle environment requires more than 1 week. In contrast, our improved multi-particle environment takes only 20 hours. The code is available at the given website. These results are exciting, but as you might correctly point out, this is nothing like our typical multi-agent environment. And you are certainly right, this is far from the real world. And this is where embodied AI comes in. Existing embodied tasks do work in photorealistic environments, with the aim of transferring learning to the real world. However, many works focus on frameworks and approaches capable of addressing only single-agent systems. Hence my call to all of you. Don't ignore the multi-agent setting. I think it will become increasingly important going forward. To demonstrate that we are indeed already capable of addressing some visual multi-agent reinforcement learning tasks, in a collaboration with an amazing set of collaborators from AI2, we extended the AI2 Thor environment to deal with multiple agents. Specifically, we developed the first simulation engine which has capabilities of handling more than one agent. Agents are visible to each other as cyan-colored cylinders, and the top-down view on the left is only for illustration and not available to the agents themselves. What the agents see is only the first-person view that you can see on the right-hand side. With this multi-agent simulation framework at hand, we can now deploy multiple agents with local views of their virtual world. We then went on to design a task so as to study collaboration between these agents. Specifically, we want 2 agents to first navigate to a specified target, in our case the TV, which doesn't require much collaboration. To encourage collaboration, we added the component of lifting this TV. Hence, the agents need to execute a pickup action at the same time while being positioned opposite of each other with the TV in between. None of the agents alone can pick up this heavy TV independently. Hence, they have to collaborate with each other in order to succeed at completing the episode. This is a quick run-through video of the task I just explained. With our multi-agent extension of AI2 Thor, we instantiate 2 agents as cyan-colored cylinders. Agent 1 is marked in red, and Agent 2 is marked in green. I re-emphasize that the top-down view that you see on the left is only for illustration and isn't provided to the agents. The agents only see their respective egocentric views, marked with red and green boxes on the right. The white triangles denote the viewing direction of the agents. So the red and green agents are tasked to first find the target television and then coordinate the joint pickup. The red agent gets initialized close to the TV and is quick to find it. The thick white line that you see in between the room is actually a wall with a door. The green agent is stuck on the wrong side of the wall and ends up banging its head a few times. It gradually finds the television on the other side. Notice how the TV is now lifted in the air. What would probably help here is a way for the red agent to signal some information. Just like I would shout out to a friend, "Come over here, I can see the TV," or "Ready, steady, pickup." We do incorporate such an intuitive communication in our model, which I'll discuss a little later. In summary, the task has two components: navigating to the target, and then a collaborative pickup by the two agents. A pickup is successful if it satisfies three conditions. First, both agents need to be near the TV, and they need to look at it. Second, both agents need to execute the pickup action jointly, together, as the TV is too heavy to be lifted by one agent individually. Third, the agents need to be on different sides of the TV so as to avoid that it topples over. The conditions for joint pickup and being on different sides makes collaboration even more important, as these conditions do require some amount of communication. The rewards we use are specified on this slide. +1 for performing a successful joint pickup. To encourage succeeding as quickly as possible, agents obtain a negative reward of -0.01 per step. A failed pickup is penalized more heavily, and other failed actions like running into a wall are also penalized. For now, we use standard asynchronous advantage actor critic training. That is no innovations on this side. Where we do innovate is on the policy function. As mentioned before, we want the agents to communicate with each other, and that's where we change things up a bit. I do want to say that this is only a first step, and I think a lot of improvements can be included in this stage. We use a convolutional neural network to process the image observation. The history of the previous observations is captured using the hidden vector of a long short-term memory network. Using the current observation and this history, the model generates what we refer to as a local belief of an agent, that is H tilde. This is where we now introduce a new module, the communication and belief refinement module. This module receives and sends messages between agents. It also refines the belief H tilde by taking into account the communicated messages from the other agents. This gives us a new refined belief H hat. This goes through another round of communication and belief propagation to generate the final belief of each agent H. The final belief H is used to estimate the state value V via the critic and policy pi. These estimates are functions of the parameters of this model and help train these parameters via a combination of an actor-critic loss and a cross-entropy loss via imitation learning. The cross-entropy loss is calculated with respect to a shortest path planning oracle agent. Since the agents are homogeneous, the parameters of the model are shared by both agents. Note that the agents can communicate using two stages. We call them the talk stage and the reply stage of the network. Both of these are identical in structure. I'll refer you to the paper for more details on those two stages. Instead, let me show you some results. Here, we present the setup without explicit communication. That is, we are not using the discussed communication modules at first. It is the same video that I showed you earlier. The one where the green agent wasted a lot of time by banging its head on the wrong side of the wall. So without communication, it took the agents a total of 165 steps to complete the task. In this process, the agents failed to pick up the TV 6 times, which is marked by red and green dots along the agent trajectories. If you missed it earlier, pay attention to how the TV gets lifted. With explicit communication, the agents complete the task almost twice as fast as compared to agents without explicit communication. The green agent does explore the environment by wandering around a little bit, but it doesn't remain stuck on the wrong side of the wall for as long as it did before. Also, there are no unsuccessful pickups, so explicit communication is indeed useful for the agents to collaborate. Note how the TV gets picked up. In this example, without explicit communication, the agents wander around a little bit and reach the target in 72 steps. They do attempt and fail at pickups 4 times during the episode. Note how the TV is finally lifted in the air after a successful joint pickup is executed. When the agents communicate, they can do the same task in just 17 steps and have no failed unsuccessful pickups. We also experimented by making the agents invisible to each other. We called this without implicit communication. Note, we depict the agents for illustration purposes only so that we can understand where they are. By taking away implicit in addition to explicit communication, we see a significant increase in time to complete the episode and also in failed pickup actions. We quantify the effect of communication in these results. On the x-axis is the number of training episodes. On the left, we plot percentage of successful episodes, where higher is better. In the middle, we plot the number of unsuccessful pickups per episode, where lower is better. On the right, we plot the number of opportunities where a successful pickup was possible, but the agents didn't attempt a joint pickup. The red plot, that is, with no implicit and no explicit communication, performs the worst in all metrics. The orange and the green lines correspond to only implicit and only explicit communication. Both the communication methodologies help individually and also when combined, which is the blue curve, which performs the best across all metrics. So to conclude, implicit and explicit communication jointly gives the best results. Please note that all the qualitative and quantitative results I showed so far are on unseen environments. That is, the environments which the agents never saw during training. Note that in reinforcement learning, many existing works train and test on the same environments. Here, on the left, we show the results on the seen environments, and on the right, we show how well we generalize to unseen environments. With the exception of no communication, all the agent ablations reach around 100% success rate on seen environments. We do a good job on the unseen environments, where the trends are similar to what I showed before. That is, implicit and explicit communication helps, both when deployed individually and jointly. On this slide, we want to quantify how difficult collaborative tasks are in the visual world we introduced in this run. For this, we translate the visual world to a grid world where information about each grid cell is available in a clean form. That is, no computer vision is needed or deployed in this setting. Green denotes free space. The blue arrows show the position orientation of the agents. In orange are the TV or target occupied cells. And red are inaccessible due to furniture or walls. Purple cells are padding cells which are outside the environment. On all the metrics we have discussed before, we find that the grid world is much easier to solve. There's a difference of around 20% in the success rate of these agents in the visual world and the grid world. Providing additional clean information such as depth maps does help improve the performance of visual agents. With this quantitative study, we conclude that environments requiring visual processing are different and more difficult than simple 2D environments. Hence, collaborative visual multi-agent reinforcement learning presents a new direction for interesting future research. In summary, we introduced the first multi-agent simulation framework for photorealistic environments. We introduced a find and lift task which is inherently collaborative in nature. We proposed a reinforcement learning framework with a partially observed state, policy function, and environment interaction. In addition to a synchronous actor-critic reinforcement learning-based solver, we make learning more efficient using imitation learning techniques via cross-entropy losses. We define the policy model, which is a two-body network processing visual information. It communicates with other agents and estimates the value and policy in the critic and actor head. We devised modular communicating blocks, which also help refine the belief of the environment. I refer you to the paper for those details. In addition to showing improvement in performance, we statistically and qualitatively interpret the messages that get transmitted between agents. I also did not talk about this here, and I refer you to the paper for more on this. We also showed results on different metrics and generalization. Finally, we established how collaboration in visual environments is a much more difficult problem than in a simple grid world environment. As I alluded to multiple times earlier, independent sampling of actions for each agent doesn't permit to realize high-rank joint probability distributions. Intuitively, the outer product of two vectors results in a rank 1 matrix. Similarly, the outer product of two vectors representing probability distributions results in a degenerate joint probability distribution. Not every joint distribution can be represented. In the TV lifting task that I just introduced, the joint probability space is reasonably small and the interactions between the agents are mostly confined to the end of the task. Hence, the issue of not being able to represent all possible joint probability matrices isn't as severe. But what if we want to increase the difficulty level significantly? What if we require intricate collaboration between agents? To study this, in ongoing work, we significantly increase the action space, as well as the interaction that is required between the agents. Specifically, we are now asking agents to collaboratively navigate a cluttered environment without dropping the TV. This task requires agents to reposition themselves during navigation such that the TV doesn't topple over. Moreover, agents need to ensure that they and the TV fit through narrow spaces. This task is significantly more challenging, and the communication strategy with the classical policy head, which I introduced earlier, is no longer able to solve the challenge in a reasonable amount of training time. Instead, we therefore develop a novel policy head, which we refer to as synchronized policies. They permit agents to interact in a much more intricate way and solve more challenging tasks, such as the joint navigation challenge. Stay tuned for more details on this work, hopefully soon, but who knows. While furniture lifting, and particularly the latter furniture moving, require an increasing amount of collaboration, they are confined to 2, 3, or maybe 4 agents. Can we train in a visual environment with more agents that require continuous collaboration? How can we learn more intricate strategies among a larger number of visual agents? This is a question that we have been looking into for a while. While doing so, we devised a novel training framework which we refer to as high-throughput synchronous reinforcement learning. We also developed novel representations that permit to train multiple agents in the Google Football environment. We refer to this representation as semantic tracklets. Instead of using imitation learning strategies, which are hard to devise, particularly in multi-agent settings, we want to take advantage of what computer vision has become really good at: object detection and extraction of semantics. I skip all the details and instead leave you with a couple of results which I'm very excited about. With that, I conclude my talk by thanking my funding sources and all the collaborators as well as you for listening. Feel free to reach out with any questions that you may have, which I'm very excited to answer. Thank you.